Cynthia, I'm going to wait, I'm going to do you about oh, good. Okay, we'll find this. You sneaked on my side, I was right. Okay. All right. Well, whenever you're ready, Addis.
Yeah.
You can go.
Okay. Thank you very much. Hello, everybody. Before I start to the presentation, just bear in mind that I'm here before 6 months ago. I'm the late comer and joined this group. So the presentation include what is in the Danube and Seine River water samples, not the major, like at the title of my page, like inventory of rare earth elements in major European rivers and lakes. So I make like a combination of Danube and Seine rivers because I have to present only this data. So to begin with, an overview of the distribution of rare earth elements and yttrium in Danube and Seine river water samples.
No. You can just click on your presentation somewhere, and now it should work.
Okay, so this presentation includes, I'll give you introduction, materials and myths, results, future activities, and finally acknowledgement. So as you know, the periodic table is classified in several groups. Our study focus on rare earth elements and yttrium. Will not include scandium in this case based on the European in the rare earth elements is the lanthanide series, scandium and yttrium, but scandium has a different geochemistry, so it will not be included in this study. So we'll include only the rare earth, the lanthanide series and yttrium. Promethium will not be included because it is a radioactive element and it does not exist in the solar system. The European Union classified these rare earth elements into two light rare earth elements, which the one like pink color, and into heavy rare earth elements. So we'll also focus on yttrium and the lower light rare earth elements. The European Union also classifies the list of critical raw materials in different, which is constantly updated in several times. So the classification in European Union in the 20 list the economical importance material, where the blue one are the one which are not non-critical, which are the non-critical raw materials, where the red one are the critical raw materials, from which the light and heavy rare earth elements that are the first most important in terms of supply risk, because they are imported from other countries or continent. They are at the higher supply risk, which are the most critical raw materials. Since this rare earth elements, this is the conceptual representation. The input, they are obtained either from mining and mineral processing, or they can be obtained from electronic waste recycling. So they have wide applications almost in every industry, like green energy devices, like the wind and the solar energy, agrochemical industries like the fertilizer, consumer products in electronics, in smart mobiles, televisions, in medical application like MRI and devices, and livestock also in feed activities, and they also apply in petroleum industrial industries. So because of this, these rare earth elements nowadays are considered as emerging contaminants because they came from either from diffuse source or from a point source. So from this application, so their source of pollution may be anthropogenic source, or it can be the geogenic source. from the anthropogenic source. From all these applications, they may go to the municipal solid waste. From this municipal solid waste, it can be distributed through atmosphere, or it can be directly moved to rivers and lakes, or they can be collected with industrial and urban influences, and they go to directly to rivers, or either they go to the wastewater treatment, where the wastewater treatment discharge contribute for the large anthropogenic source of pollution of these rare earth elements. When we see the geogenic, they can be from the mineral deposits, they can be enter into rivers and lakes through atmospheric or erosion, or through the volcanic activity. So our aim is to quantify the geogenic and anthropogenic sources of rare earth elements from major European rivers water. So from these rivers, they can be either directly used for drinking potable water, or they can be used for irrigation, and they can be has effect either health risk, or they have ecological impacts. So our aim is to quantify the geogenic anthropogenic source of the rare earth elements. Here is the sampling from the Danube River. There are 33 samples from the Danube mainstream, and 35 samples were collected from the tributaries of the Danube River, and 4 samples from in Paris during the last summer school. We collected 4 samples, 3 samples from the mainstream, and 1 from the marine tributary from the up and down stream of the Paris. The analytical methodology used for quantification of this rare earth element is the sample will be collected. After the sample collection, it will be filtered through 0.2 micrometer. It will be processed with the reference material SRL-S6 and with the method blank. After that, it will be acidified with Sopra HCl to the pH of 1.9 up to 0.1. Then hydrogen peroxide will be added to remove any organic parts. Then toluene will be added in order to evaluate the efficiency of the pre-concentration step, which is calculated by the toluene obtained through the process of pre-concentration divided by the toluene obtained after determining the toluene in the original samples. So after this one, we have original samples. This original used for either for the determination of major elements, and the other for the rare earth elements. So it will be pre-concentrated with CEPAC, C18 cartilage, which is loaded with hexyl ethyl ethyl ester. So it will be eluate, it will be collected, and it will be evaporated, and it will be dissolved with 0.5 molar HNO3 to have the same solvent or matrix with that of the used in the ICTMS with a standard. Then finally, it will be analyzed by the ICTMS. When we see the results, this is the Danube. In this case, sample of this one, there is a negative cerium anomaly and a positive gadolinium and yttrium anomaly, where in this case the pattern shows that the river is enriched with the heavier rare earth elements. So they show the same pattern. All the sampling sites indicate the same pattern where they are enriched with the heavier rare earth elements. In this case, when we see the samples in the major stream compared to see the anthropogenic effect, here in the one with in the vena, the upstream of, the downstream of the vena shows the highest gadolinium anomaly here, as compared to the Bratislava and Budapest, which is expected because this vena is more bigger than that of the Bratislava and Budapest. So here we include the ESR upstream of Munich. So in this case, there is still it is the same pattern with that of the major Danube River, but the gadolinium concentration seems higher here but the river in ESR is not as huge as that of the Danube, so it may be expected like this one. When we see the Seine River, again, the downstream of the Seine shows the higher gadolinium concentration here, I mean gadolinium anomaly. Also, the Seine River shows the same pattern, similar pattern like that of the Danube River, where it is enriched with heavier rare earth elements. Again, the gadolinium anomaly is higher in the downstream of the Seine. When we compare, even if they have different, I mean, different background, the Seine and that of the Danube, when we see that the ESR has a higher positive gadolinium anomaly, followed by the Seine downstream. So that means there is anthropogenic contribution from the city. Again, when we compare with the major, the Seine and the Danube, again, the Seine indicates a little higher positive gadolinium anomaly. When we see separately the different parts to see whether the cities contribute for the rare earth elements or not, in this case, obviously in ESR, it is the downstream one has the higher one. In Budapest, it is almost the same, like the down and the upstream. That means the contribution of the anthropogenic is less. In Vienna, the downstream shows the higher gadolinium, positive gadolinium anomaly that indicates that there is anthropogenic contribution from the city. In Bratislava, it's almost the same. There is no observable significant difference from the downstream and the upstream. In Seine, as I said, it is the downstream one has the higher than the upstream. So the size of the anthropogenic gadolinium anomaly depends on the population. The higher the population, the higher may be the gadolinium anomaly. Also, the level of the health caring system, the affordability for the MRI. That means the higher the affordability of the people for the MRI, the higher will be the contribution of the gadolinium for the river. And the ratio of gadolinium contaminated discharge from the waste treatment to the uncontaminated natural rivers. That means the bigger the river, the less will be the anomaly because it gets diluted. For example, in the case of ESR, we saw like there is higher gadolinium because waste discharge is higher than contaminated water. In the rest of this project time, we will sample the Iberian rivers and lakes in Spain and Portugal during this second month, starting from, I would say, June and July. Danube River in Serbia, it is already sampled, but the analysis is not done because we sampled it last week, but it is already ready for the analysis. Rest of major European rivers, and we'll identify the potential anthropogenic and geogenic sources in each river, and finally publish data. And it is, I would like to acknowledge my supervisor, Professor Keran Nebus, for these guys for making the map, like for the sampling map. All Jacob's geochemistry laboratory group, because it is not an easy job. I mean, to start with a new country, with a new culture, everything, they helped me a lot. Also the staff, the whole staff, starting from the security, the finance people and the like. The Panorama group, because we share lots of things, what is a challenge for everything. The European Union, obviously for the financial, and University of Gondar, Ethiopia, it is my former university. They are giving me a study leave to come here. Thank you very much.
Thank you so much, Addis, and thank you for doing the presentation, actually, because I know you were nervous that you weren't here for a long time, but you did it, and it was good.
Yeah,
it was very interesting.
Yeah.
I don't know if there is maybe some questions from the crowd. Antonios, yes?
I have two questions. The first question is, why did you do spiking with thulium in the sample?
This is to evaluate the efficiency of the pre-concentration procedure, because during the pre-concentration procedure, it will be evaporated and redissolved with that thing. And there are two. After spiking with thulium, we took the original one, we analyzed directly without passing the pre-concentration step. So to the pre-concentration, it is processed with the pre-concentration step. So what we did, this used for the evaluation of the pre-concentration procedure, the efficiency. So in this process, one goes to pre-concentration, like it will be passed with the cartilage, then it will be diluted with 6 molar HCl, like around 40 ml, then it will be redissolved again, evaporated and redissolved. So finally, it will go to the ICP-MS. So we don't know, we are not sure it is used for the analytical control of the efficiency of the pre-concentration. And we have original one that does not go to this step, that is directly analyzed with ICP-MS. So we can be sure that the pre-concentration step goes properly. So in this case, we got from 98 up to 100 efficiency of that, the thulium.
For the pre-concentration, why did you use thulium specifically?
Sorry?
Why did you use specifically thulium for this job?
I think it mainly analytical and in procedure it is they used the thulium one.
So you read it in an article, for example, that they did this.
I'm not sure.
Thulium has the lowest geogenic concentration of all the rare elements. So you have to actually add the least.
So it was because of the limits.
Thulium doesn't, I mean, there's no application of thulium. There is no biogeochemical reason why thulium should behave differently from the other rare elements. It has the lowest absolute concentration of all the rare earth and yttrium. So if you have to actually choose what you want to use as an internal standard to determine the yield of your pre-concentration procedure, it's thulium that you use. When we developed the method, we checked using praseodymium and thulium to make sure that there is no fractionation during the pre-concentration method, but then it turned out that in a specific pH range, there is no fractionation, so there was no need to have two internal standards. So we restricted it to thulium, and that worked very, very nicely.
Thank you very much. I don't know if there's some more questions from the crowd. If there was your hand, no, it's all good. Okay, well, thank you very much, Alice, for your presentation. It's excellent. Okay, so just now the work package 1 members. So I think it's Delphine, Fidel, Carlos, Michael, and Andrew that are here now. Rosa will show you the room when you're going to have the meeting. Yeah, the meeting was only at 3, but if we start another presentation, I don't want to interrupt it. So you can get settled in the room, know where it is. And if you want to come back here to follow before the presentation, it's also possible. So I invite you to follow Rosa maybe, and we will start the next presentation. Okay, Andres, so whenever you want, you can start.
Okay, good afternoon, everyone. My name is Andres Cardenas. Today I will present you rare elements and another trace element behavior and distribution in all uranium mine in Portugal. First of all, I will talk about the objectives of this project. Secondly, I will explain the study area. Then I will tell you about the methodology I use in the water sample and soil sample. After, I will explain the preliminary result, and finally, the next step of ongoing work. The objectives of my presentation is, the first is the geochemical and mineralogic characterization of the street sediment and soil sample. Second is the study the rare element behavior in water, soil sample, and street sediment. And the last one is the understand the heavy metal and rare element distribution along the Castello River and all uranium mine. My study area, you can see, is in Portugal, in the center of Portugal, specific in the Mangualde region. The mine is Quinta de Obispo mine. It is the all uranium mine. The main geological context is granite rock in different type of the grants, and you can see three different two squares in the Google Map picture, in the Google Earth picture. I will explain later what is I mean. This is this rectangle. So the methodology, first of all, I want to explain you a little this, because for the soil sample we divided in three areas. The soils. The first correspond to the waste rock, is all the waste rock inside of the ore mine. The second is the sample inside of the ore mine, but doesn't belong to the waste rock. And the last one is the sample outside of the ore mine. The second type of the sample we collect was street sediment, and the last one was the water sample. We did three different campaigns. In the first campaign, we collect 10 soil sample, 3 water sample, and 2 street sediment. I want to say something very important. After the second campaign, the EDN started the active treatment system in the mine. For this reason, we will have some variation in the second and the third campaign. During the second campaign, the EDN removed the toil soil in one of the areas of the old mine. We changed some points, some sampling point we collect in the first campaign, and in the third campaign, where EDN start the active treatment system in the open pit. For this reason, we decided to collect the sample in this campaign because we want to compare the rare element behavior and the heavy metal concentration before the active treatment system in the open pit and after the active treatment system. In the next slide, I will try to explain you how is the new rare element behavior after the active treatment system. Okay, let's come back this. The second campaign, we collect 17 soil sample, 5 street sediment, and 7 water sample. And the last one, we collect 7 water sample. Regarding to the soil and street sediment methodology, we collect 1.5 kilograms of the between 10 and 20 centimeter deep. After this, we put in the oven at 30 degrees and we separate the less than 2 millimeters. With this side fraction, less than 2 millimeters, we use one for HRD for the mineralogic characterization, and the another part we use for the different side fraction. Our goal is separate the soils in 63 micrometers and less than 2 micrometers, and check the different concentration of the rare element. If one side fraction have the higher rare element concentration, if this concentration is related with the mineralogic characterization. For the water sample, for the soil, we use ICP-MS analysis and INA, and for the mineralogic characterization, for now, we use HRD diffractograms. In the next month, we will start to use the SEN and another technique. Regarding for the water sample, we collect the sample and we filter in the fieldwork and 0.2 micrometers, and acidify in the fieldwork, and stay in the fridge until analysis. For the water sample, we collect some parameter on site like electroconductivity, pH, temperature, OD, and oxide reduction potential. In the lab, we did the chemical analysis. We analyzed the sample, the total concentration and the soil concentration by ICP-MS. Regarding to the result, we divided in two groups. The first group corresponds to the soil and street sediment sample, and the second group is the water sample. Let's start with the soil and street sediment sample. You can see in the screen all the soil sample and the different behavior in the different campaigns. Something important, we collect the first campaign in fall and the second campaign in spring. We can see different variation, and also the second campaign include more sample in age group. Additionally, I will explain you age different rare element patterns according to the methodology, because we divided this in three big groups. The first group is in the waste rock pile. You can see where is the
pointer? I think we don't have the most.
Okay. We have the first campaign, and we divided the waste rock in two subgroups. The first group corresponds to the positive European anomaly, and also the second group is the negative European anomaly. You can see we increase the sample in the second campaign and have the similar behavior. The behavior doesn't affect so much for the different season, but we did the HRD characterization, and we can see the first group with positive European anomaly have the uranium trace element. For this reason, we suppose the behavior and the higher concentration of the rare element is related with the uranium minerals, and the negative European anomaly is related with the feldspar and plagioclasa from the parent materials. Also, it's very difficult to find what is the parent materials from the waste rock, because the mine company put all the waste rock and the ore rock during the mining activity in one specific zone, and we have mixed all the material in this zone. After the wearing process, it start to create the new mineral, but most of the mineral is similar to the geological context. The second group is the rare element patterns in the old mine. It's very important. This sample was the most important for our study inside of the old mine, but unfortunately for the remediation activity were removed, and we need to find another sampling point similar with the similar characterization. But this sample had the higher amount of the better uranium minerals and the best uranium phase, and also have the middle rare elements concentration than the another sample. The QV6 is the lowest ones. We have some problem with the technique. For the reason you can see these patterns, but here you can see exactly the same. QV13 is close to the QV8 and follow the similar patterns and the higher rare element concentration. And the another sample is the bit group with the normal minerals similar to the second subgroup from the waste rock, and QV6 have exactly the same lower rare element concentration. The last group is outside of the old mine. In the first campaign, we collect two samples outside of the old mine. They both are in the different location, have the similar rare element patterns. We suppose this pattern is from the parent rock, and also the sample correspond to the similar geological unit. And in the third campaign, we increase the second campaign, we decrease of the sample of the amount of the sample, and have the similar behavior. And this part correspond of the street sediments from the mining, have the lowest rare element concentration. We decided to include this slide because it's very important to know what happened with the street sediment. specific in the second campaign because we increased the amount of the sample. KB4 correspond to the sample from the street sediment from the open pit. You can see the pattern is totally different than the other street sediment for the river. We suppose this contribution is for all the waste rock because during the mine activity, most of the another part of the waste rock was put inside of the open pit, but the mine company before didn't remediate all the mine and start increase the phreatic level, and all the open pit was full with water. For this reason, EDM start to do the active treatment system. Okay, now I will move on of the water sample. You can see this is the open pit from my mine, and this is the Castello River. For this, I want to talk and you see the different variation. We have two groups of the sample, three sample. This group of the sample correspond inside of the old mine. We have the similar conductivity. Also, the pH is between 0.5 to 5.5. But this group is the water sample we collect in the river. The pH is higher and the electroconductivity is lower. It's the same with the oxidoreduction potential. In the second campaign, I will explain a little more about these chemical parameters. And the second in line, we have the sulfates. For this part is from the open pit, exactly the same, and this behavior. Q11 is the one water sample we collect inside of the old mine, but this sample doesn't have contact with the water from the open pit. For this reason, the behavior, the chemical parameter are so similar, is so similar to the water sample. So for the rare element patterns in the water sample, we can divide it into groups. Exactly the same of the chemical parameter. We have this group correspond of the sample inside of the old mine, except KB11, because I explained you before, is different behavior. And also this sample have the higher rare element concentration. And you can see have one negative European anomaly, and this have the positive European anomaly. We are studying, we are going to study this part more in detail, but from the river, you can see the pattern is quite similar and the concentration is more similar for the river rare element patterns. Okay, I will explain a little of the heavy metal distribution in the old mine. You can see the different sampling points inside of the mine. And we select uranium, thorium, iron, and nickel because the mineralization of the old uranium mine obviously is uranium, and also we have chalcopyrite inside and manganese oxides, the secondary mineralization. You can see KB4 is the sample from the open pit, have more distribution in uranium than the another. It's very the nickel concentration. Is from the motifs from the parent rock, increase the amount, but the rest of the sample have the lower uranium concentration. KB11, I told you before, have more iron concentration because the micas from the geological units had higher amount of iron. We analyzed and we found this result, but the rest of the element is lower. Also, it's very important, this concentration is the zone doesn't pass of the limit from the European standards of the water sample. Is very clear the distribution because I want to see better. For outside of the mine, we have three points, one upstairs, one in the middle before the water go to the river, and another downstairs. you can see all the distribution of the metal is very similar. We don't have any apport from the open pit to contaminate the river, because the concentration is more focused for the contact between rock and water. The second campaign, this campaign, we collect the sample after the beginning of the active treatment system. The main purpose of the active treatment system from the open pit is increase the pH, and EDM put some components inside of the open pit, the pH increase, but after this, they put 2 pounds for this pound after they across the treatment, stay for long time for the precipitation some metals. After this, the EDN put the water in the river. You can see before the distribution, one of the good point is the pH increase in all of the samples. This sample is from the open pit. The pH is around 10, because then put one base in all the water from the open pit, and this is very close, and the electroconductivity for this sample go down for the active treatment system. And as you can see the next slide, we have exactly the same, one group and the higher pH from the open pit. Now, if you can see the radical element pattern, before we have 3 samples in this part, but in this campaign, we can separate very clear like the first campaign, because the active treatment system affect the radical element pattern and decrease the concentration of the radical elements and decrease the uranium concentration in most of the points. Let's see the heavy metal distribution. As you can see, before we have the higher amount of uranium in this sample, and now we only have 8%. This is more similar to this sample, exactly the same. And this, we continue the same. We don't have so many uranium. Before is 25% of the uranium, now is 1%, and here is 36%, 38, sorry, 38%, continue the same, but this sample start to, the heavy metals and the radical element concentration were down. For the outside of the ore mine, we have the similar patterns like the before, because this point don't affect from the open pit. Okay, the final marks. The first thing is the soil sample with uranium phase show a higher radical element concentration and different radical element patterns than the other sample. The second is the soil sample outside the all uranium mine have the similar behavior and mineral phase. I explained in the last slide what is the reason they have the similar behavior. The street sediment have the similar patterns in both sampling campaigns. The water sample divided into 2 groups according to the chemical parameter and radical element pattern. It's set after the active treatment system. The water sample inside the all uranium mine have the higher uranium and radical elements and trace element concentration before the active treatment system. And the water sample outside have the lower trace element concentration and don't show the real contamination due to the mine waste. Ongoing work. As you know, I was in Rennes for 4 months. I did so many experiments. I came back from Rennes the last 2 days ago. I didn't run the sequential extraction in different soil samples because we want to see the fractionation on all the fractionation in the radical elements and uranium distributes around of the all uranium mine and inside of the mine. I did the leaching experiment with one soil, and we check in different pH scale. We are working in this paper. We will publish in September, October, and also we have one preliminary paper. We are waiting for the approval. And the geochemical modeling, we will do 2. I start to do the speciation modeling with the radical elements along of the river, and for the leaching experiment, we will do the surfaces sphere complex because we want to see what is the mechanism between the solid phase and liquid phase, and what happened in the transport between these two phases. After I will finish the side fraction separation, less than 2 micrometers, and I will do the salts characterization by center. Thank you for your attention. I'm so sorry that.
Thank you very much, Andres. I see we already have some questions. So Fidel, if you want to go.
Yeah, thanks for the presentation. I have 1,000 questions, so maybe better meet for lunch or for dinner. I guess that the main objective is to see the transfer of rare earth from the solid to the water. So basically, the results tell that most of the rare earth in the solid waste stays there forever, right?
No, for the leaching experiment, we have like the almost 25 or 26% of the transport from the solid phase to the liquid phase in the small amount. If you quantify this in big amount, I will do it this because we collect 1 point in the real life and we do it in the experimental life, and we will compare what happened in the experimental part and what happened in the real life.
But you don't see this in the
No, because I am going I am working in this. I finished the last Monday. Yeah, I talked with Remy about the percentage of the transport, but we want to see the mechanism of the transport between the solid phase.
And another thing, I saw some distribution plots, so it's showing 55% of uranium.
Yeah.
Really?
Yes.
So you should be careful with the radiation then.
We measure this because from the zone analysis, the company requests this, but the radiation is not high because it's natural uranium, and I work with 1.5 kilograms. Is the absorption, I don't know the name, the absorption capacity for me is very low. I can work without any problem.
So you have a concentrate in the sample, half of the sample is uranium.
Yeah, much of the,
It doesn't care if it's natural or from a nuclear reactor, it's uranium, basically. It's to create the uranium also very fine. And okay, and the rest is nickel.
yeah.
So I guess you have a nickel mine in the sample.
No nickel mine is more for the minerals because we have some higher amounts of the nickel in the sample from
Yeah,
the
it's a lot, it's a lot.
Yeah, it's a lot. It's more like the iron.
Okay.
Probably not all the elements are analyzed. This is something.
No, we analyze all the elements, but we select this heavy metal because it relates with the minerals.
Yeah, but I mean, the 50.
Yeah, it's no.
Is it refers to the full data set?
No,
only
from the heavy metals.
Okay,
No,
okay,
from the
okay, sorry. I was trying to scare it.
Yeah, I won't show
No,
that.
please show it. I mean, maybe I understood wrong, but yeah. And the other thing is, well, the redox in the river is extremely. I mean, something or sometimes means nothing. So a river with a very low or relatively low redox probably means nothing. So especially for further calculations, it's really hard to use this low redox in the river because which is the redox pair. Maybe it's not redox pair.
Yeah.
And the final issue is, and this is general for all people here, is what heavy metal means. What means heavy? Because all metals you show are heavy. So and there are many others. So all metals are heavy in this respect. So I suggest starting non-using the word heavy. Just use metals.
Okay.
Because it's a word that we have used for long and it doesn't mean anything. Thank you.
Thank you, Fidel.
Why is that so?
Well, define heavy metal.
Yeah, but why shouldn't we define them anymore as well?
Because it means nothing. I mean, my principle in science that using the same that others did in the past is not always correct. So we need to improve things. We need to go. We need to do better things. And if the others in the last 100 years use heavy metal, this doesn't mean it's correct. So using heavy metal, it's heavier than platinum. Is the iron. So what do you call it heavy iron? You have a lot of metals that are heavier than iron. So just telling heavy metals, well, we have more than a half of the same.
Thank you, Fidel. I don't know if there is a more question. Yabuki, go ahead.
Very nice presentation. I was wondering if you already have in mind the surfaces that you want to take into account for geographic modeling, or
Yes, yeah.
you deciding it?
We try to decide it because we need to complete some results because was one problem with the equipment. And after we see the result, we will decide if we will do the all in complex or the another. But now I did the speciation, but I didn't show because I didn't have time for do all the interpretation very well.
Thank you.
Okay.
Yes, Michael.
You refer to the soils.
Yeah.
What about the organics of the soils?
We didn't mention because my approach is not the organic. However, for the leaching experiment, we measured the organic matter because probably the organic matter had one in the higher pH used from the rare element used the organic matter for the transport and so on, some colloids. But in my PhD is no, we decided we don't use the organic matter. But for this point, we decided to include in the leaching experiment because we take the soil, we measure the organic matter in different pH, and we will check what happened with the organic matter in this soil only.
How much organic matter is in these soils?
When the pH increase, the amount of the organic matter is between 30 to 120 milligrams per liter in the higher pH, but in the lower is only 20 milligrams, 20 ppm.
Thank you very much. And maybe some more questions from the crowd. I'm sorry, I'm hiding over here. Maybe some more questions from the crowd. So now you're good. Okay, I think it's all good. Thank you very much, Andres.
Thank you.
Okay, whenever you're ready.
Okay, then. Good afternoon. Well, most of you know me. I'm Marcin Plachciak. Well, my supervisor which just left are Dr. Fidel Grandi and Dr. Carlos Luis, and I will talk about rare earth elements in phosphate industry, from raw materials to environmental impact. So basically, the content of my presentation. First, I will talk about the phosphate industry in Spain generally, then the decalcium phosphate industry. Then I'll briefly say something about the objectives of my work. I'll proceed to the characterization of the fluoride sludge. Then I will talk about the potential extraction and the fluoride sludge purification. I'll proceed to economic assessment, then to next steps, and finally I will conclude. So Spain for a long time has been, well, historically has been a home of the phosphate industry. There are, well, some fertilizers are produced in Spain as well as the decalcium phosphate. The main sites are found in Huelva in Andalusia, like in southern Spain. Also Cartagena next to Murcia, and Flix in Catalonia. There are two main ways to produce the phosphoric acid. You can treat the raw material, the phosphorite rock, with the sulfuric acid, which is the way on the left, and the products are phosphoric acid and the phosphogypsum. And there is a way to treat it with the hydrochloric acid, and you have the phosphoric acid plus the residuals, what are called fluoride sludges, which are shown here on the right. So basically, the raw material which was used in Spain is mostly from sedimentary origin. So it's presented as fluorapatite or francolite. It's enriched with some radionuclides from uranium series, such as uranium-238, thorium-230, radium-226, and polonium and lead-210. It also contains quite significant concentration of rare earth elements, which could be then passed over to some of the products. In case of the sulfuric acid way, we have the phosphoric acid, which is then turned into fertilizer, which on most of the uranium and thorium is partitioned into the phosphoric acid, while the phosphogypsum is mainly composed of gypsum. It has around 95–96% of gypsum, and most of the radium, polonium, and lead are fractionated into the phosphogypsum, as well as the rare earth elements. In case of the hydrochloric way, we have the phosphoric acid, which is then turned into decalcium phosphate, which contains some of the uranium and most of the lead. While we have the two types of residues. We have solid residues, which are mostly calcium fluoride, which is the mineral fluoride. Most of the uranium-238 and some of the lead are fractionated with solid residues, as well as all of the thorium and polonium. While the liquid residues are mostly composed of calcium chloride, and they contain the radium-226. So what actually is the decalcium phosphate? It's it's usually produced and used as an additive to an animal feed, like mostly in chicken farming, but also added to some of other food products. And in Spain, as I mentioned, they have used the sedimentary phosphate rocks, mostly from North Africa, Morocco, or Tunisia. And it has the calcium phosphate is produced in some of the plants, which after processing all the phosphorites, they're putting all of their fluoride sludges, all the waste, into the landfills, which are basically which are just next to the factories. As I mentioned, these residuals have some uranium and thorium inside, as well as some other radionuclides. So they are considered the NOR material, which is the natural occurring radioactive material. And we were mainly focused on two of the sites in Spain. One in El Hondón in Cartagena, which is a legacy site. They stopped producing the calcium phosphate around 2001, and we have around 1 million ton of sludges in ponds and piles. And we also have Flix in Catalonia, which is still active and is producing around 50,000 tons of the sludge for year. Here we have, you can see the maps. The one above is the fish site, which is collective, and the one below is the aluminum. So the main objectives of this work were to make the characterization of these ways of the fluoride sludge from these two sites, determine the pathways of the earth elements, if they are going to solid or the liquid, and which mineral they're actually available, and to assess some of the potential waste reduction and try to convert it to a byproduct. So among the characterizations that we have done, well, we have used several methods. We have used the X-ray diffraction for the mineralogy. We made the analysis of the particle size. We made the analysis with the scanning electron microscope to see some of the phases. For the earth elements content, we have used the ICP-MS. And also a couple of weeks ago, we have performed the synchrotron beam analysis. Here you can see the diffractogram of the flesh sample, and it shows the fluoride as the most abundant mineral. But as you can see, it's quite different. That the peaks from fluoride are quite different than the rest of them. They're quite broad, and it could be related to the extremely small size of the particles of the fluoride, which are, well, some of them are even smaller than 1 micron. So these results could be quite underestimated, and it could have even more of the fluoride. In case of the sample from Melondon, it's similar to the flesh, but we have found gypsum as the most abundant phase, which was quite weird. But this site is characterized by some other waste as well. We have some pyrite ashes present next to the phosphate mass, as well as some waste from demolition of some buildings. And it was quite hard to drill it, so we have taken the sample from first tens of centimeters of the soil, so it could be contaminated by some gypsum. Then here we have the particle size analysis, and actually almost all of the particles have a size less than 10 microns, with 65% below 5, so they are extremely fine. Here we can see the picture of the stem, and these round crystals, like round bright crystals, are fluorides. So you can see quite a lot of them. The scale is actually 1 micron, so you can see how tiny they actually are, and they are quite abundant. And on top left, you can see the gypsum just as a comparison. And later, just to see the crystals better, we washed them with some distilled water. We did a centrifuge, and then we put it with a tiny drop of water into the graphite sticker, so we can see it better. And here actually it's the 10 micron. The scale is 10 microns, but you can see the grade is much better. And if it comes to ICP-MS, here you can see the characterization of the concentration of earth elements in the raw material, the phosphoride and the fluoride sludges. And basically, we can see that they are much more, they're really enriched in the final waste. There is a hypothesis, we made a hypothesis that is the fluoride precipitation that takes all the rare earth elements, which could make sense looking at the concentration as well. The lanthanum is more than 300 ppm. So if we take into account all that there's more than 1 million tons of these wastes in the landfills, the concentration, the amount that could be potentially extracted from there is quite big. So it could be taken as the secondary source of all these rare elements. Also, yttrium is not it's not actually here, but it was more than 0.5% in the fluoride sludges. And here we have the comparison of the fluoride sludges from the landfill, which are the blue, and from the second decantation tank, and in the factory of where they produce the decalcium phosphate. the wastes are going through 3 different decantation tanks. So basically, they are like retreated with the hydrochloric acid just to increase the efficiency. And we took the sample from all these three tanks, and they are really enriched in comparison even to the fluoride sludges from the landfill. But the lanthanum has more than 800 ppm and neodymium more than 600. Even well, most of them are more than 100. So the concentration is quite significant. So if we wanted to extract them potentially like as the secondary waste, it's possible to combine it with to start extracting it already from the factory, not digging out with the landfill, and it could be really probably profitable to the company that we wanted to implement it, and well, it would reduce much the waste. Here we see the secondary waste. We took some samples from these 3 tanks. We had them. Well, there were some of the fluoride muds and some of the liquid, and we took both of these and measured the concentration over Earth. They are normalized for the North American shell composite, and as you can see, the concentration in solids were more than 3 orders of magnitude higher than in liquid. And in liquids were some of the PPBs, even PPTs. So the concentration was extremely small. So you can see all of the rare earth elements are actually fractionated into the solids, not into the liquid. Okay, here we have some of the analysis of the synchrotron. We have used the Lucia beamline in Soleil, and we have performed some mapping of the micro X-ray fluorescence in spectral analysis, and we have found some of the neodymium into the fluoride phases. So we are pretty sure that this is a fluoride that's actually capturing all of them, and is the host mineral of the rare elements inside. We had quite some difficulties because of the matrix effect. Even though there's quite a big concentration of lanthanum and cerium, it was hard to distinguish it because of the other peaks with the same energy range, like titanium and vanadium. Also, they weren't, in this beamline, they weren't quite used to work with the calcium in such a huge concentration. And the peak was actually really, really intense, and it was hindering to detect some of the other elements. And since our sample was mostly calcium fluoride, it made some difficulties. But here you can see the spectrum fix. There are 2 regions around here and here that was missing some elements, and after including the neodymium, you can see the fit. Well, it fits much better to the experimental data. So we are pretty sure that there's a neodymium there. Here we can see some of the other sample. Well, it was actually more like a hotspot. The scale is in microns, so it's tiny, 25, 30 microns. And we had the same situation. We have found the neodymium inside of the fluoride. You can see here and here, it was the same thing as for the samples before. Also, we have performed some of the experiments for the potential extraction of the rare earth elements. We have used flotation for that, since, as you remember, the particles were tiny. They were going with the air phase to the froth, while leaving all the other waste behind. And I have some video of that. Fluoride. And if it comes to economical assessment, Addis mentioned before that rare earth elements are, according to the European Union, in the highest supply risk, since all of them are basically imported from China or other countries. And it's estimated that some of these elements will actually even multiply. Well, the demands will multiply. So taking it from the secondary sources as the fluoride must would have much economical sense just to lower the dependence on the other countries, and just to well, also it is truth what Michael said, that we would have to send it to China again anyway, but at least we would have the sources of some of them and slightly lower the dependency. What are the next steps? We took some more samples from Flish, actually, of the groundwater and of some solids, and we'll do a chemical characterization. Then when we have all the data, we will develop the reactive transport model, which will help to evaluate so if the rare earth elements have some environmental impact, and assess the potential extraction of the rare earth elements. Well, we still have to finish the analysis of the synchrotron data, because we haven't actually received all of them yet, and we need to process it. And to conclude, well, all the rare earth elements which were inside of the raw material was actually fractionated to the solid phase, to the fluoride sludges. As I mentioned, the fluoride is the host mineral of the earth inside, which is quite stable. And well, the preliminary results don't show any environmental impact of the rare elements on groundwater. And since the fluoride is quite stable, we don't think there will be any impact. And if it comes to the extraction, well, the initial stages of characterization showed we have some nice opportunities for the recycling to convert it to a byproduct and diminish the amount of residues, while increasing the amount of rare earth elements which are available to use in Europe. And well, if not the rare earth elements, also the fluoride as well is a critical raw material. So if it would be really hard to extract some of the rare earth elements, also fluoride can be used as the material which could be sold, reducing the amount of waste. But we would have to perform some other experiments on a larger scale just to see if it's profitable or not. And that's it. Thank you.
Marcin, can I ask you to stop the screen sharing?
Sure.
Perfect. Okay. I don't know if there is some questions in the crowd. Yeah, just like that. It's all good. No questions? I might have one, but you know, I was in and out, so maybe you said it already. Regarding so you mentioned that European Union's goal is to achieve at least slightly better independency in terms of resources. Yes. How are we on that track? Do you?
I mean, well, they're not so high concentration that we would definitely be independent of everything. So, but at least introducing some of it would actually help. And if more companies started doing that, it will be much better in achieving that. But with these kind of secondary sources, there's no way to be dependent from
Fully.
Okay. China.
Okay. Thank you, Marcin.
Thank you.
Any questions? Maybe you were inspired. Okay, so we can stop for now. As I said, we have some time ahead of us, so if you want to take a break and grab some fresh air, and now's the time. Maybe come back at around 3:30 because that's the initial timing that I gave for Professor presentation. Maybe it will be a little later than that, but at least you will be around. Thank you all. Bye-bye.
Thank you.